Record to the cloud. Okay. Good afternoon, everyone. My name is Nathaniel Frizzell, call sign W2NAF, and this is the HamSCI biweekly telecon. And today I would like to welcome Alec Engell, who's going to be talking about an ecosystem called Panhelio. So Panhelio is an ecosystem for collaborative and repeatable heliophysics data processes, sciences, and forecasting. It brings state-of-the-art data access and analysis to heliophysics data types to streamline science. Panhelio's goals are similarly aligned to Pangeo's goal, except for heliophysics. One, to foster collaboration around the open source scientific Python ecosystem for the solar, interplanetary, magnetospheric, and ionospheric sciences. Two, to support the development with domain-specific helioscience packages. Three, to improve scalability of these tools to handle petabyte-scale data sets on the high-performance cluster and cloud platforms. We'll demonstrate Panhelio by how it is used to predict solar energetic particles, or SEPs, and discuss current efforts to make Panhelio scalable to solar imagery data and to make it available to the heliophysics community, HamSCI included. So with that, I would like to welcome Alec Engell. Take it away.
Great. Thanks, Nathaniel. Thanks all. I've been on the HamSCI email list for a couple years now, so I think I've been tracking, I don't know, about 60-70% of discussions on that. So it's nice to put some faces to the names and call signs or whatever you call them there. So and Nathaniel, thank you for the opportunity here. And so let me just go over to the screen. So what the intent here is today is to run through these slides relatively quickly. Let's keep this informal. I'm really just interested in the discussion once you guys start to see what we've used, quote, this Panhelio for, and where we look to make it bigger and better for the community. And really what it needs right now is it's useless unless it gets used. So advocacy and things like that are what we're after beyond our science objectives for our specific efforts. So with that, a little bit background of the company I work with. I've been at NextGen for about 5 years. My background is in solar physics, mainly observations and solar eruptions and things like that. NextGen is a DoD IT company, enterprise IT company. And so we've grown significantly over the past 5 years since I've been here. I think there were 30 people when I was hired. Now we're approaching 200, if not at 200. We're all over the United States here with some of the offices. I'm the dot in Montana, and we have other remote workers as well. Just screaming through, this is a NextGen is awesome slide. You guys have the recording, so I won't belabor this slide. Okay, what we do, ignoring the contract vehicles there, that's more for partners to identify where we can collaborate on. But the services that we do are software development, systems engineering, cybersecurity, T&E, program ops, solutions, mission planning, C2 decision aids, architecture modernization. A lot of that needs to happen across the DoD and space weather, I would argue as well. And then R&D, that's where you see some of our stuff such as machine learning, AI, space weather, and whatnot. So that's just a really high level introduction to NextGen to give you some context, where I, a space solar physicist / data scientist, has teamed up with the software engineers and the like over at NextGen. All right, so some of the key takeaways here, you heard Nathaniel say this twice already, but it's an ecosystem for collaborative and repeatable heliophysics data processes, science, and forecasting. Why? Well, we want to bring state-of-the-art data access and analysis to state-of-the-art heliophysics data to streamline science. How do we do this? APIs, databases, widgets, collaborative ecosystem, using some of the technologies mentioned on the right, such as timescale, database, REST APIs, Python APIs, JupiterHub, and the like. You also have the ability to bring in external data, right? I can give on JupiterHub, on the sprints, on the Panhelio hub right now, I can give Nathaniel 100 gigabytes to play with and say, hey, put all the radio data that you'd like to fuse with all the solar flare, X-ray, and proton data that we have there, including the ACE and Discover magnetic field information and plasma. And so he can go in and import that data, upload it directly to the hub, and do some data fusion there. So it supports anything like that from any types of files. So probably not too much of a surprise there. If you're working in a Python environment, you can do data fusion. Likewise, you can do machine learning and processes and the like. And then what's great about this community, heliophysics, is that we've really taken a step in terms of adopting open source, and leading the way, of course, is a lot of the Python libraries out there. So SunPy, very open general library for doing solar physics processes, some space physics as well, but mainly solar focused. PySat, SpacePy, PlasmaPy, Chianti, which is an atomic database, Komodo, which has ties into running physics-based models at the CCMC. That's NASA CCMC. And then, of course, all of this is cloud native. And if it's cloud native and you're using libraries that are built to scale, then you can scale. And so that's sort of the what, why, and the how of Panhelio. All right, so it wouldn't be a presentation from NextGen if we didn't have an architecture diagram. I think these things are generally overlooked in the field when people start off on projects or when they want to try to modernize their current architecture. So on the left, it's no surprise you have that's your data coming in. So right now, we focus on a lot of the NOAA SWPC data. That's the operational data, since our use case for using Panhelio is to predict solar energetic particles. So we have ingestion scripts that pull from their different files, whether they're netcdf or whatever. And then we run event detection algorithms that identifies flare start and end times of SEPs, start and end times of solar wind structures. And that's data-based into our timescale DB right there. And then you can have tie-ins to the model data from the CCMC using the Donkey API, which is a CCMC developed capability. Or you can go through Space Weather Trek, LASP, that's been developed out of LASP, and you can use the Lattice API. And then you can use the Sun API. So basically, the long story or the short version is that you can organize all these different APIs, understand which ones pull in similar things, identify which ones you should use, which ones have best practices, and start to organize really for the community. Like, hey, you want this type of data set? There's an API that's already out there that does that. And that's the whole idea of this ecosystem, is trying to organize a lot of what's already out there into a best practice environment for streamlining data access and fusion. And then some of the other data types you might not be as familiar with, but you have the Virtual Solar Observatory, Heliophysics Data Portal. You also have the JSOC in there. The HEC is the Helio Event Knowledge Base, some more metadata type of stuff like, hey, I have an active region on the sun. It's automatically detected using computer vision and things like that, and that's where they pull a lot of their metadata from. And then you have the SHARPs, which are basically magnetic fields from active regions there. And then you can pull all that in, and you can access it from the Python API that can tie into these other APIs. What I'm describing right now is probably the least developed aspect of this ecosystem right now. The most developed is certainly the operational ingest coming from NOAA into the timescale database. To speak briefly about the hosted data silo in there, you could foreseeably have SMEX missions completely in the cloud. So for instance, some missions might have 30, 40 terabytes in their prime mission. And you say, you know what, I want all of that in the cloud. I want that organized in such a way in the right formats where people can really do some streamlined data science and some science analysis, depending on what type of data that is. And that's the idea of having that hosted silo right there. And that's an example of like the upcoming Punch mission, which is a pretty cool mission if you're unaware of it. So anyways, shifting over into the Panhelio Hub, JupiterHub, Python, R. If it's a Python environment, like I said, you can do data fusion, machine learning applications. But what's really gets me going on this is that you can deploy operational tools, analysis tools, using a bouquet server, panel, and things like that. So you really can do all of this from within the environment. And you can, within the JupiterHub, I can do PRs and whatnot to my favorite code repos, and go about it that way. So a lot of this is self-contained in this environment. And you can provide these types of, you can provide the JupiterHub or these sort of dashboards via bouquet server to operators, forecasters, scientists, but also STEM, also REU students, crowdsourcing, maybe applications for HamSCI. And then last but not least, you have the Python libraries that sort of make everything go here. So on the left side of this top bar here, you have more of the domain heliophysics specific libraries, PlasmaPy, SpacePy, HelioML, Chianti, Komodo. And then more on the right are your more generic data science libraries that are pretty state of the art, such as Xarray and Dask and Bouquet. So that's the architecture. I think that's important to present in terms of what we're looking at moving forward here. Are there any questions on this before I move on?
I think there are some. Go ahead, Bob.
I was going to say, what does a timescale DB refer to? What's specific about?
If you just look up timescale DB, you'll find it on the internet there. It'll describe how it's a relational time series database.
Okay, so it's just that it's relational and time series.
Mm-hmm. Yeah.
Okay.
And I'm use Jupyter notebooks and Jupyter Lab all the time. But can you talk a little bit about what JupiterHub and the Bouquet server is?
Yeah, we'll do. Yeah, that'll be part of the demonstration that I have outside of the slide deck here.
Great.
Yep. Cool. Yeah, feel free to interrupt anytime, guys. So already talked about this, the parallels to Pangeo and Panhelio, they're very similar. So we want to keep aligned with this on top of what I already mentioned. I will note though, this is probably worth mentioning, Pangeo was really developed by a lot of smart scientists out there that say, hey, we want to create these packages, Python to do this and scale all of this stuff, and that's great. But a few years in, they want to go back and do their research. So I think there's a little bit of struggle right now to say, okay, let's hang up or at least pump the brakes a little bit on our efforts to organize Pangeo in the community and more, hey, I want to get back to the research. And I think this is where you might get improvements if you were to take lessons learned from Pangeo and apply them to Panhelio. Say like, hey, we need buy-in from agencies to support this, right? So maybe this is a NASA type of deal with industry support and then scientists really filling in that third part. So really not everybody, not one group, not academia just doing it, but agency, academia, and industry working together to try to make it happen. Because I think Pangeo is struggling a little bit with just academia doing it currently. So for what it's worth. Okay. So what are we using Panhelio for? So forecasting SEPs. We have these requirements from the Air Force. They want us to predict 10 MeVs at 10 PFUs, 10 MeVs at 40 PFUs. The 10 MeVs at 10 PFUs, mainly like polar cap absorption type of stuff. So things that this community would probably be interested in. But the other stuff is mainly high flyers, single event upsets on satellites, and things like that. Human exploration too for NASA. And this is what we're after. So that's, we organized, we have the architecture, we have the data in mind that we want to do this. So with that, I'll go ahead and jump right to the JupiterHub demo here and the environment that we just work in. So give me a second here. I'll expand my screen. Right, so here's the JupiterHub environment. I'll just zoom in here for a moment. So this is my home page. A lot of this stuff is like, hey, if I feel embarrassed about the way I'm going to initially tackle a Python notebook or data fusion, maybe I won't let the rest of my team see it, and I'll just develop within my notebook here. But most of our team's efforts are under the shared notebook here, or the shared folder. If you go into data, this is that free floating data cache I was talking about. So Nathaniel, here's your 100 gigabytes that's allocated to you, where it might be CSV files or whatever. So I have a bunch of different catalogs in here, and I'll get to the importance of catalogs and sort of one of the focus areas that we had up front in the project, because we've been very frustrated with this community, or at least I have, in terms of solar event catalogs and the lack thereof, or not the lack thereof, but actual, there are way too many and they're all over the place, and a lot of them are very wrong. So it's crazy that this community does not have sort of a collaborative effort in best practices for developing these associated catalogs, this flare to that SEP, to that CME, to that shock, to that radio burst, to that event on Earth, right? It doesn't exist. All right. So this is our team here. So we have a few people from NextGen, some folks from NASA, some other research teams on here poking around and seeing how useful this is. This is my notebook here. I did a lot of data preparation type of stuff. But just to say, you know, what you can build with this, what we focused on were the staple space weather in situ measurements. So GOES, X-rays, protons, electrons, and the ACE and Discover solar wind data. So that's really what we focused on databasing in this project and creating a Python API. So Nathaniel, to give you sort of an example, once your script is, this is our event graphs in here. This code in here is basically what we use to deploy our dashboard. And then if I go to new, open a terminal here, provided everything is right, the terminal opens up and I give it basically these two commands. And these two commands basically access those Python scripts I just showed you. And this is what you get out of it without diving into the code. So here you're met with our main dashboard. We have it automatically pull up the Halloween storms here. And so I don't know if you guys have a favorite event or anything like that, but to give you a sense of the usefulness of this tool, is that first, it's interactive and you can interrogate the data very precisely. So I can go ahead and zoom in on the x-axis here, and we can take a look at you know, the flare that occurred here, X-rays at 1 minute cadence, the protons here at 5 minute cadence, the shock arrival, you can see some ESP particles coming, and then, you know, the sheath of the CME, I guess, right here. And so you can jump to any date between 1985 and present using this. Moreover, you have the ability, provided your privileges are there, to associate events to other events. So I just clicked on this data column, this data table right here, and you'll notice that this flare became highlighted in red, and this SEP event became highlighted in red. That means that we have in our database, these events are associated with each other in our database. I haven't gotten to the event association of the solar wind yet because we're focused mainly on predicting the SEPs, but you can go in here and I have the ability to change the latitude longitude. If somebody says, hey, I have this et al. Paper that says the latitude longitude of this solar flare was not -16, -8, it was something else. Well, okay, great. I'll go in here and I'll change it. And maybe there's a way to even annotate and cite the et al. Paper. And so somebody else comes along and thinks that it might be wrong, they'll see the et al. Paper or something like that. So that's the idea of creating sort of a community-driven, hey, this event is associated to that event, and so on and so forth. And then say you don't agree. There are plenty of people who have different definitions. Noah Swipsey having one of the oddest definitions, I would say, of SEPs, meaning that the SEP level has to drop below 10 PFUs, and that's that cross line there highlighted in the plot. So if you basically get an event and it goes down, and then another solar flare that's associated to it, or a CME shock that's associated to the SEP again, and it doesn't go below that 10 PFU, that means that SWPC has assigned that one flare to basically two different SEP events. And that's fine. You just need to know what the definition is. And we created this database as well so you can do version control of this as well. So if you come in and say, hey, people have different definitions or whatnot, then those can be implemented. They can work off of, so Nathaniel works off of NextGen version 0.1 underscore Nathaniel or Scranton or NASA, whoever. And then the idea is hopefully we get to an agreement where we're 90% of the way before people make their own derivatives of those catalogs. But I think this has been sorely missed in the community in terms of a way of doing it. You know, emailing people and getting catalogs and CSV files is great, but not streamlined at all, right? So I think with that, this just shows, you know, and again, this is all done in Python, all deployable within the JupiterHub. That's another just key point to re-emphasize for you all. And the fact that we can create these data tables and use these data tables to edit what's in the database highlights how powerful I think the capability is. And just to give you another sense of, you can create these however you want. So for instance, if I click on in the data table here, this CME event, it highlights eventually, there we go. Oh, there's a little bit of a delay. So we have just a 3D plot for fun that shows BY, BZ of the CME solar wind as it passes by L1. And so you can, again, whatever analysis tool you would like to see in any dashboard, you can generally make it happen. We found very few limitations. One limitation, for instance, we couldn't do a log linear plot in bokeh, but actually they just released today a fix for that. So I think there's that. So this is the main time series tool. Again, it's all of the solar wind data. If I click on near real time, it'll take us to the near real time, or should. We're working on that solar wind data gap there. So that's being addressed presently in our current development sprint. But you can see here, we'll have some of the SEP forecasts from our capability to be able to compare them against SWPC and things like that. So I think that's all I had for the main dashboard here. And then I just had one analysis dashboard to complete sort of the demo. And then I'll just have a closing remark or two regarding to how we're trying to democratize this capability for heliophysics. So any questions on this sort of dashboard presented here before you guys?
So
Okay.
Bokeh is the software that you use to create these dashboards?
Yes, yes.
Okay.
Yep, Bokeh with panel together, yes.
Mm-hmm.
Yeah.
Are there any questions from the group?
Okay, so this is what I call the analysis dashboard. In the ideal world, I would have this pulled up side by side with the time series dashboard. So just to give you a sense, let me go to the time series plot here. So these are all the flares that we registered from in our database, which it looks like going back to 1975 through present. And you can see that these are just all the solar flares, and you can clearly see the solar cycles. You can see maybe before 1981, the X-ray data seems a little bit dicey. It doesn't seem to have quite the pattern you'd like to see. So you can interrogate the data this way. Eventually we'll have this plot, so it'll have red circles where the flare has been associated to a solar energetic particle and things like that. But in this plot, there are I think 70,000+ flares, and you can see that it handles that data size pretty well. If you get into the hundreds of thousands, there's something called data shader, which works very well for seeing patterns and without necessarily displaying each glyph.
Excuse me, Alec, I have a question.
Yeah.
The flares, are these every flare that was detected, even if it didn't hit the Earth, or are these ones that hit the Earth?
Yeah, so all flares hit the Earth with what's measured from GOES. If it goes off on the disk side facing Earth, I think this is actually from the NOAA SWPC catalog. Our catalog does just straight up event detections of the GOES data, and I actually compared it with the NOAA SWPC catalog as well. But we wanted not a human in the loop determining the start and end times of the solar flares. But yeah, generally if the flare goes off and it's on the disk facing Earth, then we'll see it. Even if it's on the limb, if the post flare loops of the active region get above the limb, you'll pick up some of the X-rays, but it depends also like what the background of the sun is. Like if you have a bunch of sunspots on the sun and you get a flare, you know, you might not pick up that flare because it doesn't go above the background.
Okay, thank you.
Yep. So again, why did our project focus on the GOES X-rays and protons? Other than it's a very complete data set, meaning going back to 1975 in this case, but we actually cut it off at 1986 because of data issues potentially before then. But that's a relatively complete data set if you want to take a data-driven approach for predicting things. So a lot of people talk about high resolution, you know, SDO data and things like that, but that's only been up there since 2010. So you're cutting out quite a significant amount of events. And when in our database for 1985 through present, we really only have about 230 so SEP events that have been associated to solar flares. And if you want to use those solar flares to predict solar energetic particles, they're associated. And I'm not saying solar flares cause solar energetic particles. It's really the CME shock that does for the most part. But if you take that approach, you really want the biggest data set. And so it's, again, GOES X-rays and protons are really a staple data set for this approach. And so we can see from these histograms, you know, what our distribution is. The Air Force is interested in, you know, hey, I want to know in this 6-hour window, what's the likelihood of getting a 10 MeV, 10 PFU event? And then so on and so forth. So here are the different AFRL requirements. And we want to look at our statistics. And when you get out to 72, 84, 96 hours, our statistics are terrible. So if you try to do probabilistic forecasting for those types, you know, take it with a big grain of salt. And really what we hope to do in the future is to do a time series, a machine learned time series model, rather than sort of this event prediction capability, which we're currently focused on. And mainly that's because that's been what's done in the field currently. So you can just get an idea for the event associations here. Scatter plot matrices are a great way to understand, you know, multidimensional data sets. So the blues here are the flares that have not been associated to our SEPs in our database. The green circles to red circles are flares that have been associated to SEPs. So it provides you a good snapshot here. And some of the flare parameters that we're using to predict the SEPs are peak of the flare, the fluence of the flare, where did the flare go off on the sun, what is the ratio of the long and the short channel of the solar X-ray flare. And those are the parameters that we are putting into, actually we put into pretty much every single machine learn model in scikit-learn, plus a couple of others. And the idea was to run 10K, tenfold cross-validation on them to be pretty robust, see which models are the best. And you know, that's the nice thing. It's a very repeatable way. And if I go in using that time series tool I just showed you guys, and I edit one of those events to a different latitude, longitude, or I say, hey, that event was not associated to this event, or I change the start and end time of the event, as soon as my machine learning counterpart opens her notebook and runs her model, that's in the database. So that's ready to go out of the box for her. I don't even need to tell her I did an update unless I say, hey, Brianna, I really like you to rerun the models because I changed 20 different events based on new definitions or corrections. So anyways, almost done here. More data science visualization tools. Parallel coordinates is great. Some of the parameters I mentioned here before. So ratio, decay phase of the flare, where the flare went off on the sun. So longitude, the flux of the flare, and then the fluence of the flare. And the idea is you want to see that separation of the blues, the flares that were not associated to SEPs in our database, to the lines green to red, designating the flares that were associated to SEPs. And in this case, the color table here is shown by your typical NOAA SWPSI scale, your S1, S2, S3, S4, S5. S1 is 10 MeV at 10. So about here, that's your S1 event and your S2 event and so on and so forth. Never had an S5 event. And then on the right, sort of just a 3D plot, nice to look at. And again, as a data scientist with some background knowledge in this, you're trying to give your machine learning expert sort of a leg up. Hey, Brianna, I think that these are the most important parameters out of the 10 or 12 that we have. So when you do your analysis or you drop one of those parameters and then you rerun the model, you know, just keep that in mind. So trying to complete that. That's sort of the complete approach as far as we take it here at NextGen. You know, provide visualizations as best as possible in multi-dimensional space, so the machine learning expert at least has some tools and methods to work with there. So I think that's all I had in terms of you know, our specific use case for Panhelio. But like I said, there are a lot of other things we'd like to extend it to. I'll mention just briefly. Nathaniel, I'll just take 6 more minutes and we can open up for discussion or whatever else you guys have on the agenda. So we know in heliophysics, we get terabytes and terabytes of data. From SDO, we get roughly 1.8 terabytes of data a day. Those lovely FITS files come down, people go in and request them and things like that. But those are in FITS files, and really the best way to access these FITS files, at least using these Python open source libraries such as Xarray and Dask, is to have these files in either netcdf or ZAR format. So you can do that. Of course, you're essentially duplicating the data, but when they are in that format, you have the ability to do all these different annotation tools on them. So I can do all sorts of analysis, and this is what we're trying to gear up towards. We're partnering with Anaconda on getting Xarray to actually work with the world coordinate system. It currently works great with geospatial and things like that, but it is generic enough as long as we just implement the world coordinate system into Xarray. We should be able to do this stuff with solar imagery and other heliophysics data where we were not able to do before. And that basically opens up a whole lot of streamlining analysis capabilities, such as, you know, there are just many that you could do. And what we'd like to do is create a general dashboard where the community can look at like, hey, that's good. Doesn't quite fit my purposes, but I think I can probably, based on what's available, you know, tweak it there and there, and I can get it to work this way and that way. And that's sort of the idea behind working with solar imagery and turning our attention to that a little bit more. Again, trying to widen the audience that might be interested in Panhelio, because right now, Xarray unfortunately doesn't support world coordinate system. And so right now you're looking at not latitude, longitude, but you're looking at pixel space of SUVI. But once we get it in there, then your analysis becomes true to the coordinate system, and then you can really start to do the science. So yeah, there's that. There's a few other things, but you know, I'll stop there because, like I said, I'm interested in sort of what you guys are doing, how you guys look at something like this, and just general feedback. So Nathaniel, thank you. Over to you guys.
Well, thank you very much, Alex. I really appreciate it.
Yeah, you bet.
It's nice of you to spend this time with us. Yeah, I have a very nice presentation, and I have a couple of questions that I might kick things off with, and then we can turn it over to other people. One thing I noticed, you have a tremendous amount of solar data in there. What about ionospheric data, things like ionosons and superdarn and other maybe like in situ ionospheric measurements? Do you have any of that in your system?
No, unfortunately, this certainly where I want to take this, right? Like,
Mm-hmm.
I went for what I thought was foundational space weather data sets, and now I'm like, all right, we're looking at imagery. Okay, we got that, but hey, we got a stick. Let's shake it out there and see what kind of opportunities we can do to bring that into a database like this. In situ data is so small.
Mm-hmm. True.
So if we focus on in situ data and create sort of that baseline foundation of space weather data from sun to the mud, that's in situ data that a lot of the field uses, then I think you're really cooking with fire, right?
Mm-hmm.
But we have just not had the opportunity, nor do I really have the experience to say, hey, these are the data sets that we should pull in from ionosons and things like that. Looking for excuses, Nathaniel. So if we can find an opportunity to do that and sort of make a more complete picture for that, I'd be game.
Right. You mentioned a number of things where you mentioned the CCMC a number of times. What sorts of collaborations do you have going on with this CCMC right now?
So right now it's relatively straightforward. We developed this for forecasting solar energetic particles, but the architecture we found that we developed has a much wider application for the community as possible. So we've told CCMC that, hey, might be something you might want to consider. And that sort of led us to a discussion with the heliophysics data enterprise being led by Brian Thomas, Jack Ireland, among other folks. So we're currently in discussions with them because they are right now, I think they're calling it the Heliophysics Data Research Library or something like that, basically a modernization to their heliophysics data enterprise current capabilities. And so we're trying to see if there's an interest for NASA to work together, because we think we have some of the solution that they may be looking for, and we're currently in discussions exploring that. So I think, again, when I kicked off the call, I think something like this it's not just industry doing it, and it's not just an agency doing it. It's really everybody together, especially in the field of heliophysics when it goes across multiple agencies and the like.
Yeah. Right. Have you talked with Masha at the CCMC about it at all?
Yes, I have. She's been on the call where I sort of presented, and to give you more information than probably necessary, but we originally called this effort SPRINTS, the Space Radiation Intelligence System, and that was to do forecasting of SEPs. But when I presented it to CCMC, Masha was on the phone, I believe, Layla. There was a little bit of confusion, like, hey, Alec, you presented forecasting SEPs, but then you presented sort of this other thing that you were claiming was, part of the innovation that you were doing. It's like, that's true. So we're calling now Panhelio the ecosystem, and Sprints is really the application tool or system that we developed for forecasting SEPs. But cutting to the chase there, Masha is very well aware of, there's a paper submitted to Advances in Space Research by Rebecca Ringette, and she works at CCMC, and it's basically calling for, I think it's called diaries, but it's calling for something like sprints, and it actually calls it out in the paper that says sprints, aka Panhelio, is the closest thing. And that's basically what the paper is calling for the community to adopt. And Masha read that paper, and so there's a connection there as well.
Yeah, that makes sense. Let's see. What about, are you familiar with resin at all, that reproducible space physics environment? How does your ecosystem relate to that?
I am familiar with it as much as I've read on black and white. I have not experienced it under my fingertips in terms of working with the software or anything like that. it's a tool that is interesting. It's been shown to me, or I've been pointed to it. I've read up on it, but we just didn't take the time yet so far in this effort to see where one piece can fit into another and so on.
Yeah.
So I think there is something there to be explored for sure.
Yeah. Yeah, that would be interesting. I think one of the things that's challenging, for us as a community, and I think you kind of hit on this at the beginning when you were saying that the Pangeo people, they were really excited about the data analysis tools, but then they want to get back to research. It's like, it takes a tremendous amount of,
yeah, I got
effort.
you. Keep going.
Hi there. It takes a tremendous amount of effort to learn one of these data analysis ecosystems or toolkits.
Right.
And we also have to make sure that we're, productive writing papers and actually pushing science forward. So it's like trying to figure out which is where it's, what the thing to, where it's like really worth your time spending on that.
Right.
So I was just kind of curious how it interfaced with all of those different things. What about let's see. So if you were us, how would you recommend we get started with this? And like, what would be a good use case for the ionospheric physics community?
Right. So to give you an example, I showed this at the Punch meeting, and a grad student or a postdoc says, "Hey, I'm working on solar imagery to really bring out coronal loops and things like that." So we're like, "Hey, we'll IP whitelist you. We'll tell you that you can bring in as much as 50 gigabytes of data within the JupiterHub, and you can sort of use any notebook in there to help with initial plotting or data fusion using our API and things like that." So I can suggest a similar thing, like, hey, identify a really foundational data set for you guys, or data sets, that you might be able to do some, multiple plots comparisons to goes and things like that. We wouldn't be able to database it under this effort, but you certainly could bring in your CSV files, and those CSV files combined with our Python API, you could do whatever sort of data fusion process and analysis that you think would be interesting. So that's one suggestion, I guess, Nathaniel, but I'm certainly open to IP whitelisting a few of the folks at HamSCI, and certainly available to give you guys some gigabyte room.
Yeah. Do you let's see, do you have kind of crib notebooks to get people started? So if someone says, I've got this event that I'm looking at where we're looking at the impact of a solar flare.
Yeah.
Do you have some sample notebooks and analysis tool chains that you'd be able to set someone up with and kind of walk them through and say, okay, here's how you get started with it?
Yeah, to be honest, yeah, that's relatively straightforward. We have a bunch of notebooks that, hey, you can pull in the continuous measure. Yeah, so we do have that for sure. Depending on whether it's event focused or sort of a time history chunk of like 10 years, we can do either or. But yeah, all of that's relatively straightforward to set up, a very generic notebook by just really riffing off of what we already have.
Yeah. Are there any costs for these services?
There are. So what I showed you here runs NextGen about $500-$600 a month. And we have about a terabyte worth of data, of in situ data, actually probably closer to 600 gigabytes for all the goes data. So that's to give you a sense. We worked on actually a soil moisture machine learn project called SMART, for soil moisture something clever. And we, at one point, because we were doing machine learning in a neural network, we had 30 terabytes on what was it, like the most expensive data hosting platform on Amazon. So it'd end up being like thousands of dollars a month for the period that we needed to do the machine learning training. But so that's what it. But again, if you start with in situ, and I think a lot of you guys are focused on in situ stuff, and that's why I'm sort of keen on understanding what could be a foundational type of use for you guys using this.
Yeah.
You know, it's not very much, so you can make it happen. And
Yeah.
and just to give you a quick sense of, you know, what else we built this for, again, the geospatial tools are pretty much ready to go. And so in our soil moisture effort, we had 3 data types: soil, geology, numerical weather model, and satellite. And so in here, this is basically the notebook here that you create, the Python notebook, and then directly from this notebook, you can launch it as a dashboard. And so here I'm creating a new dashboard called Soil and Geology. And here is basically the display of all NASA's SMAP data, which is roughly about 400 gigabytes worth of data. It's created in a netcdf file, but then you have all these annotation tools. So if I go in here and if I select, you know, an area that we did machine learning at, you can display all this. And within this notebook, there's probably being accessed about 2 terabytes of data. And then likewise for the, this is numerical as well. So just the efficiency of using Xarray, Dask, netcdf, or a ZAR format together. And you guys do some geospatial stuff. So some of this stuff is certainly relatable, but this is more on the what we used it for the earth science side. You know, pick a point, you get a time series type of deal in a second, and then you're able to do the analysis there. And then here's satellite, so MODIS for you. So just to complete the picture there.
Right.
Alec, I got a question for you. You keep saying that in situ data doesn't amount to very much. What are you talking about?
Right. I knew I'd get in trouble for that one.
I mean, we take terabytes per day sometimes.
From the satellite, right? Yeah, I guess I'm
Well,
more
from
referring-
radios. Any radio, if
From
you're
radios.
fully digitizing, gives you
Yeah.
tremendous amounts of data.
Yeah. Well, I guess. Yeah, it's not as much as imagery, but you know, again, I'm not in your field, so I'm sure there's going to be more in yours. So again, that's why I'm more keen on like what completes a picture for you guys. Is it all of these? It's all of these streams, right?
Yeah. Do we have a budget, so to speak, or a daily burn rate for the personal space weather station?
In
What we're
terms
expecting
of
to take per day?
in terms of amount of data,
Yeah.
um,
I'm not even sure what our bandwidth is and whatnot that we're
it's
expecting.
highly variable because the personal space weather station model is essentially very dependent on what a person is able to, what their particular bandwidth pipe is and what they're able to afford. So we don't, and so the personal space weather station is supposed to be the low cost one is supposed to be a very limited amount of data, whereas the Tangerine can produce again terabytes per day.
Yeah, I'm not talking about low cost. I mean, that we're just taking audio data and
Bill, you have
analyzing it for a very low data rate.
What did we plan for?
Okay, I wouldn't say that, I don't believe that we actually have a plan for how much we're going to expect. The thing is that my experience is that most of the people who are going to be running the Tangerine are going to have a DSL connection with a very limited upload bandwidth. So that's going to be more the constraining factor than anything else for most stations. Now, in terms of, you know, I can get tens of terabytes added at the snap of a finger when we decide we need it for the central control system to collect data. However, I guess we shouldn't be wasteful with it. I mean, if most of the information we want to look at is included and constrained in an 8 kilohertz sample, which for the Doppler data, generally it is, that's what we should collect. Now, there'll be other science measurements, you know, experiments you want to do that are going to where you're going to want to collect enormous amounts of bandwidth, but you're going to be constrained on how much you can actually upload to any central point, regardless of how much.
Well,
data capacity
DSL is not the limit. I mean,
Yeah,
I've got 600 megabit per second wireless in the house.
I would,
I'm talking about I'm talking about what can go up to the central control system. That is limited by DSL for most users. And DSL for me, I can upload.
I don't know
maybe
anybody who
up to
uses
megabits per
DSL.
second. Say that
I
again.
don't understand.
Well, there's one here.
Well, but a lot of us are, most of us are cable or fiber.
Yeah, DSL is all you can get here.
That's all you can get here.
I
All
think
right, well.
I think the answer, maybe a better answer would be, I would expect to run campaign to run in a normal mode, say on the order of tens to 100 to 200 megabytes per day per station, and then do a burst mode where you'd have much higher, where you could do a
Right.
triggered sort of event where you could do much higher rates.
Yeah,
But,
that's the sort
yeah.
of thing we do.
Yeah, I would expect, your standard, the standard data product to be tuned to around somewhere between tens to 200 megabytes per day.
Yeah, and when you
First
run a
station.
campaign and collect a lot of data, and if it's just a campaign, you can upload it and it could take a month to do the upload, and we can do that.
And I do think, I think it would actually be very interesting to do a survey of what people's actual connectivity is, because it just anecdotally from
That would
listening to
be-
these telecons, certainly people who live in urban areas, like I've talked to Bob Gerzoff here about his internet connection. They are able to get high-speed cable and high-speed high-speed cable, high-speed fiber, but
Yeah.
then it seems like
Well,
a number of
But
Yeah.
that's not urban anymore.
No.
New Hampshire and Vermont are very well covered, and increasingly so with cable and fiber. I mean, Vermont has had a very large initiative that gets all of the rural areas covered with fiber.
Yeah,
Not the country, however.
AT&T
But,
will never
but
run
my
fiber
point
here.
is that we
Not
can
in our
generate a
lifetime.
tremendous amount of data. That's one of the things we need to design in the personal space weather station is forms of data reduction so that we can get it down. We also, what we do with our Dartmouth research is we have like daily summary plots that's what actually gets uploaded to a server somewhere. And then if we find something interesting, the raw data has been stored locally, and we go and grab it.
Yeah, we already have that arrangement working with the Tangerine prototype localhost. The way I do it is I run GNU radio, and I have two digital RF outputs. One is just 3 kilohertz around where the Doppler is where you're looking, and the other one is wideband. Well, actually,
Right.
one of them is actually about 10 hertz wide. That's what I'm uploading today. That's reduced.
Right, well-
Then it's what you said.
Yeah.
and those things they're able to be adjusted, so we'd be able to
Yeah.
make one wider or one less, and we have a ring
Right.
buffer going, so a person could potentially have a terabyte ring buffer if they spend enough money on their local system, and then that data could be requested.
Well, it also begs the question, why are we working on a 10 gigabit per second Ethernet if we don't expect to be able to get that data anywhere?
Well, that we also have the ship the hard drive method too.
Well, that's
So-
what I'm saying is we
Yeah.
store it locally,
Right, yeah.
but
So-
that data is going to be generated, and ultimately people are going to want to keep it in the cloud somewhere. If it
But
becomes of research interest, it's got to go to the cloud somewhere.
yeah, so I mean, the current, so we have the software mechanisms in place to control that amount of data and how much gets sent. We can throttle it back, we can expand it. So we have those mechanisms in place from a software perspective. And the back end from a software perspective should be able to handle it. In terms of the actual amount of storage that the back end data servers are going to have, that's not technically within the scope of this current grant, because the current grant is just for prototyping an initial
Right.
like small, so we don't really have the capacity for a large
Yeah.
scale at this point. But
Well,
that
right,
would-
but this
that
is
would have to be-
anticipating once it gets deployed and we start getting actual
Yeah.
usable data, I'm just warning you, it's going to burgeon very quickly.
Mhm.
And saying that, you know, our in situ data doesn't amount to very much. I know from our own experience that just isn't true.
Yeah, I agree with that.
We're going
I
to
think-
need a large server
Well,
somewhere.
now bear in mind also that what we are working on with this phase of the National Science Foundation grant is a feasibility demonstration, like a prototype concept. If the decision is made that we're going to roll this out worldwide and have thousands of users, we're just going to have to include in the second phase of the program something that's got petabytes worth of storage somewhere.
Mhm.
Right.
So
Yeah.
that's all we can do. I mean,
Right.
you know, we're limited.
But
by
what
the
Alec
size
is
of the grant
presenting
now.
is that sort of a repository. So
Mhm.
I'm just saying we're going to be, if we're actually using it, we'd be putting in quite a bit of data.
Yeah, I think
Yeah.
that is something for phase two, right? I mean,
Yeah.
what we've got right now is going to be kind of limited. I mean, people always have the option to purchase their own Amazon Web Services and spend whatever they want per month to store their data. But as far as a central command system, we'll have to get some funding for that for somewhere.
I think what I'm seeing from Alec's presentation right now is I'm at least viewing it more from like a data analysis ecosystem sort of perspective, where if I wanted to sit down and do a case study or even do some sort of you know, statistical study that pulls in all of these other data sets, I'm not really viewing it as a way of holding all of the personal space weather station data. I think it almost, right now I'm seeing it more fit into like this other project that I'm working on with these traveling ionospheric disturbances doing analysis.
I will say, Nathaniel, regarding that, like you do in general for this analysis to be streamlined need the data already there. So, you know, in case of the HamSCI NSF stuff that you guys are working, if you wanted to do that streamline analysis across multiple teams, like Team X is investigating this, Team Y that, based on all that stuff. Yeah, you'd ideally want it there, and we only can do that sort of analysis on the GOES data because it's there.
And you have it on your servers, is that the
it's
idea?
It's on AWS, yeah, nothing's local.
So it's, well, if it's on AWS, it's local to Amazon, so.
That's right, yeah, it's local to our Jupyter instance and our ingest instance, yeah.
So like if we wanted to use your ecosystem, would we have to like contract with you to store all of our data on your systems, and then you would contract to AWS? Is that the idea?
In general, yes, but you know, from what I hear, what you guys need or would want in this phase one would be a feasibility study on saying like, hey, you know, we're submitting a phase two, and you know, we have the potential to get, you know, 2 to 10 terabytes of data a day. You know, here's how we're going to treat it and do it and whatnot. And so NextGen does those types of studies. And we work with our partners to do that stuff, and that would be sort of the steps to do it and understand sort of best practices and the most efficient ways to do it. But what you said is certainly in general, yes, that's what we would do. But again, we're hoping that NASA sort of buys this. And if you guys are familiar with NASA's SMCE, their Science Management Cloud Ecosystem. Put up by Dan Duffy. You know, I mean, again, I think this is where NextGen really doesn't want to hold this for anybody in particular. We're a services company.
Right.
We want to basically say, hey, NASA, take this. And by the way, you know, HamSCI is interested in using it too.
Yeah, and I think that's how I'd feel more comfortable too, is like if we were, you know, when I'm working, we have both NASA funding now and we have NSF funding, and like I'd rather work with the granting agencies and be like, okay, we need a data management plan, you know, what's the way that NASA, like I was just on a call with Masha from CCMC right before this call, and like we're starting to talk about, you know, how we would interface with the CCMC, and so like I would be, you know, very happy to figure out how to get my projects interfaced properly with CCMC. And then if CCMC, you know, said your tools were the way to go, and they provided that, that system.
Yeah, and I almost think that the advocacy also needs to come from you. You know, I
Yeah,
think CCMC does do some great things.
yeah,
They do have software engineers, but they are not a software engineering outfit, whereas
right.
NextGen is. And, you know, they do a lot of work. You know, Masha has a lot of things going on, and I'm not
Yeah,
saying they wouldn't be able to do it, but I mean,
yeah,
this is why you work with industry to basically
right.
streamline and make sure that when push comes to shove, it's ready to go. You know, I've been disappointed with some of the modernization practices that CCMC has done. I've talked to people who've worked at CCMC for many years. They feel the same way.
Mhm.
I think they've done a great service for the community, but I think they've extended a lot of this stuff. And I'm hoping this HDRL will help alleviate some of that stuff that's currently ongoing. And again, to emphasize, all the stuff that they do is great, but this is where I think advantage can be taken by working together, right?
Yeah. Bob, you have a lot of experience with large scale statistical sorts of things and software environments. Do you have any questions?
I'm still trying to wrap my head around, I know what exactly how I would use something like this. Um, when I see something like this, my thought is that, oh, here's a nice way to download a bunch of data um, that I would not normally have access to and I could probably massage it into a fashion that I can merge in with my data. I'm going to be an R user or a Stata user or whatever. So I don't see it so much as, for me, it's going to be, okay, here's a data source, and I'm going to download it so that I can use it with my analysis package. Because now maybe because I'm never going to have, or at least I don't think I'm going to have, maybe I will once we get the PSK reporter data, data that I can't handle on my desktop. And, right now I'm working with 2 million observations of WSPR data. And I'm looking at your stuff and saying, I wonder if there's some electron density that I could get that's time stamped and then merge it in with my WSPR data, or get I forget what else you had there, but I'm wondering is that a possibility already, or is
Oh
that?
yeah, it is. Like data access is definitely a part. It's not just data access to do the analysis. It's like, yeah, if you guys have local data to you that is untenable and can't put in the cloud, then yeah, all you have to do, and I presented this to the SMAP team, and I said, isn't this a much easier way for your users to download SMAP data as opposed to downloading SMAP data, NetCDF files and whatnot for globe? A person might only be interested in SMAP data for this part of the globe. And so you can code all that into these dashboards and say, and just with the Python API, you can just say, hey, continuous measurement API, download goes electrons, protons, 2 MeV, whatever, etc., down to your local, because you don't have the ability to upload your data. So it definitely goes both ways
Yeah,
on that.
yeah. I mean, I could upload. I mean, like I said, my entire data that I'm working with is, like I said, 2,500,000 observations after post processing. Now I could probably put it on yours, and maybe I could do the analysis there as well. I noticed it did say R there, and did say Python. So I presume I don't know all the terms you're using, but inner and outer joins, I presume are possible based upon multiple keys. Could be date, time, and latitude, longitude.
Yeah, we haven't focused on R a lot, but certainly that's something that is just easy to set up an environment regarding that. Yeah. And yeah, that's what I'm interested. If you guys think about, Nathaniel, if you guys think about in the next 3 weeks or whatnot, say, hey, like, cool project, 50 gigabytes, 100 gigabytes, we can make that happen for you guys to explore it. At the very least, we can make it open to you guys so you can poke around and and maybe I can give you a demo on how the API works and how to create a simple plot. And if there's a request to put up an R environment, JupiterHub can handle that too, and that won't take but half a day less than from one of our engineers. So,
Yeah, I'd take 2 gigabytes.
two gigabytes.
Yeah.
Is that
Seriously.
is this something you're interested in, Bob?
Well, I'll have a discussion with you about what the relevance, the scientific relevance of the measurements that he has are to the kind of exercise I'm doing.
Yeah.
I don't know if they would be good covariates for my models, or are they good predictors? Are they, or do we want to explore that and just see if they are, or if there's no likelihood, or if they're too far back in the causal chain. We want something that's more proximal to the actual variation. Then, but that's a conversation for you and I.
That sounds good. Yeah, we'll have a chat.
Okay.
All right. Well, thank you so much for your time, Alec.
Yeah, you bet.
What's
guys.
the baby's name?
This is Callum. Cal.
Callum?
Hi.
Yeah,
hello.
Callum.
Hi, Callum.
Not there.
No, he's just barely 4 months old, so he's just lifting his head up and getting beat up by his older brother. More of that to come, huh, bud? No, I really appreciate the time, guys.
Thank you.
So
very
this
interesting.
is just, yeah. So again, I'm hopeful that something like this can be adopted potentially by NASA. So you guys basically then put in a request to say, hey, we need X terabytes and we like using this type of capability. Again, it's not like we want to host this thing forever. We're looking to hand it off to somebody and just service it because we think there's advantages with that business model, so to speak. But I'm all for data science and data fusion, so I get excited if there's any excuse to complete the picture of space weather. Always gets me very excited from sun to the mud. So I really appreciate your guys' time, and hopefully we get some cool data to work with in the cloud with y'all.
Thank you.
Okay,
Thank
guys.
you so much.
Take care.
Take care,
Bye-bye.
Alec. Okay, bye.